Example 4 from 3.9 is a 5'6" woman is walking away from a 12-foot tall light post at a rate of 2 feet per second at night. At what rate is the length of the shadow increasing when the woman is 25 feet from the light post? So this one we're given a schematic here, and note that the yellow is showing where the light is. And so the woman's walking away from the light post and the light is shining and hitting against her back, and then when it hits the top of her head, it comes down at that angle from the light source down to the ground, and that creates a shadow. That shadow length is on the ground denoted x sub s. So what we're trying to find is the rate at which that shadow length is increasing. So with this setup, that would be d of x sub s over dt. And we want to do this when she's 25 feet from the light post, which is going to be when x sub l is equal to 25. So the given known is mostly in the picture, but we should denote what the rate is for 2 feet per second. So it is some sort of length per time, and so what we have in the picture here is this is going to be the rate at which she's moving away from the light post. So that's going to be d x sub l over dt. And that length is increasing, so it's positive 2 feet per second. Alrighty, so we'll get started on our equations in a minute, or equation. Let's first appreciate what changes with time. So note that this little picture I drew on the bottom here is the woman a little bit further away from the light post, and so x sub l is increasing, x sub s is increasing, x is increasing, the height of the woman and the height of the light post are staying the same, and also there's things like the hypotenuse of this triangle, this big triangle overall is increasing, and we don't really have any information about it. And that's important when we're trying to figure out equations. Unlike the other ones that had volume in it, which are all the examples I've done so far, example 1 through 3, the equation is not obvious in this one, or equations. So this is a challenge. When we see triangles, we usually think about the Pythagorean theorem when we see right triangles, so that might be an option. Also notice that we have a similar scenario to the candy cone one in that we have two right triangles that are the smaller one's embedded in the bigger one, so we do have similar triangles here. So it turns out Pythagorean theorem is not going to be real helpful. I'm not going to even write it out, because we have some unknowns on the base, we have some knowns on the height, and we don't know things about the hypotenuse. So introducing the hypotenuse into this problem would just be increasing our unknowns here. This is not helpful. So similar triangles looks like it's probably going to be the way to go. And I'm kind of getting ahead of myself in this one, and I should write down exactly what I need in my equation. Well, we need the variables that are either given as rates in the rate or something we're trying to find. So that would be x sub l and x sub s. So to be a little bit more specific here, we need x sub s and x sub l in our equation. Alrighty, so let's just get started here. The most obvious thing maybe I can see is with there's something with the similar triangles we'll do in a bit, but notice that the way the picture is set up, that x is equal to x sub l plus x sub s. So would this equation be enough? No, it's not going to be, because I'll get rates after the derivative for x, x sub l, and x sub s, and I really only can account for x sub l and x sub s, their rates, not the x. So that means I need another equation. So we talked about similar triangles. Let's explore that. Similar to, again, example 3, we have a smaller shadow triangle that's embedded in the larger one that's made with the light post. So we want to relate the heights, because we know those, with the base stuff. I'm going to start with filling in this proportion. There's 4 blanks here. With x sub s, that is the base of the smaller shadow triangle, and the height of the woman is 5.5 feet. So that's a place I can get started. The base of the overall triangle is x, and then the height of the overall triangle is 12. So that's great. Looking at that similar triangle proportion I just set up, that's not going to be good enough all alone, because I can account for the x sub s rate but not the x after I take the derivative. But note that if I substitute in for x sub l plus x sub s, then I'm going to have the equation totally in terms of the stuff that I can account for. So that's going to be the ticket. We have x sub s over 5.5 is equal to x sub l plus x sub s over 12. So you could take the derivative at this point, but you might want to do some algebra first and just get that reduced down as much as possible. So we will have some like terms with the x sub s's going together. So what I'm going to do, I'm going to multiply both sides by 5.5. Just kind of clear these fractions. And then what I'll have is x sub s is equal to x sub l plus x sub s over 12 times 5.5. So I'm also going to clear the 12. I guess I could have done that one step, but that just gets rid of the fractions. So 12 x sub s is equal to, and then the 12s will cancel here. So I'll have, after distributing the 5.5, on the right hand side, 5.5 x sub l plus 5.5 x sub s. So now I can go ahead and get the x sub s terms on both sides. So I'm going to subtract 5.5 x sub s from both sides. So then what I get is I get 6.5 x sub s is equal to 5.5 x sub l, and I guess I could stop there. That'd be fine. But I'm just going to go ahead and solve for x sub s, but dividing by 6.5. And so 5.5 x sub l over 6.5. I just can't stop simplifying, so I just will keep going. This we could think of as 55 over 65, which reduces to 11/13. And now this thing is really boiled down, and I'm going to take the derivative. Taking the derivative with respect to t on both sides, both x sub s and x sub l depend on time. This derivative step is actually going to be really easy. On the right hand side, we're going to have dx sub s over dt. On the right hand side we have just a constant that we can pull out, and then we're going to have this times dx sub l over dt. So finally, we're on the last step here. We're going to sub in and solve. So our dx sub s dt is what we're trying to find. Dx sub l dt was given, and that was 2. So plugging in, we have dx sub s over dt is equal to 11/13 times 2. So one thing that's a little different about this problem is we were supposed to do this when x sub l equals 25, and it might be a little disconcerting that you couldn't use that. But it didn't depend on it. And so it turns out that the rate at which the shadow is increasing only depends on the rate at which she's walking away from the light post, or the rate at which she's walking. And so that can happen, that sometimes we don't need everything that's given, or some of the constraints end up kind of falling out of what we actually needed when we sub in. So we have 1.69 approximately feet per second, and that's it.